Hello everyone, thank you for coming. Today I will be presenting to you about the efficient path planning and tracking for multimodal legged aerial locomotion using integrated probabilistic road map and reference governors. This is a work done by Eric Sihite, Benjamin Motis, Paul Genam, Ali Reza Ramezani, and Mori Garib. This is a work in collaboration between California Institute of Technology and the Northeastern University. First, we begin with the introduction. This work is done to develop a controller and path planning algorithm for the legged aerial capable robot, the Husky Carbon, shown on the right side of the screen. This robot has a typical legged actuation, so it has two actuators on the hip and one on the knee. And but in addition to that, it has propellers, which allows the robot to both walk and fly, depending on the situation. This work is inspired by animals such as the birds and amphibians, where they can traverse a wide range of terrains using either fly, walk, or swim. The expanded range of accessible terrain and the ability to choose the most efficient mode of locomotion means that the system can effectively traverse any difficult terrains and much more efficiently, saving the battery expenditures, etc. The challenge are the additional actuations, like adds more weight to the system, which means like this system needs a great we need to select components with the best power to weight ratio. The additional actuators also makes the design of a controller more complex, and also complicate the design the design and implementation of path planning algorithms. As you can see here, like most of the components are lightweight, such as like carbon fiber tube and carbon fiber and 3D printed components. And we use a very high power density actuators over here, such as the pancake BLDC and harmonic drives. Overall, the system is powerful and lightweight. So in this slide, we'll show some of the past work in multimodal locomotion and also morphing robots, as a robot can transform between legged and aerial. So in the multimodal robots, we have this robot, amphibious robot by U. So it's like we have the wheel and the propeller for underwater locomotion packed into one. There's this salamander robot by Isbert, like it has leg and also can perform undulating motion both on the ground and inside the water to propel. So there's a flying star here where there are wheels attached, and it can transform into the between UAV and wheel motion. And we have this Leonardo robot by Kim, where there's a propeller attached to the body to assist walking, and also capable of like performing something like hover jump. So there are also other moving robots, but most of them augment their existing mode of locomotion, such as over here, Revere's like has a quad rotor that's capable of rotating its propellers around. It's still an aerial locomotion, but with this morphing capability, it's capable of performing some more complex maneuvers with it. There are some other robots, such as this rolling robot, where it can open and close the wheels to vault over like certain obstacles. So we're trying to combine this kind of capabilities into one package, and that's the current work we're working in. We have a transforming robot and capable between like an legged and aerial locomotion. In this slide, we show some past work in path planning. So in this work, we use a probabilistic road map and A-star to generate our path. The same probabilistic road map algorithm that available out there is modified to work with a multimodal system. And then once the road map and path has been generated, we use an A-star algorithm to find the minimum energy path from the current to the final position. It will be explained later in more detail. So this is the outline of for our presentation. We have done the introduction. Then we're moving next to the dynamic modeling for simulation, followed by a path planning algorithm design, and then the control design. And we'll present our simulation results and discussions, and we'll finish with the conclusions. The full dynamic model for quadruped can be highly nonlinear and multidimensional. So in order to simplify it, we developed this reduced order model shown on the right. So basically it's composed of a single mass body, which is the torso of the robot. And there are like and the legs are modeled as simply a massless system. And then we use this kinematic model to find the leg end positions. And from the leg end positions, we have the ground reaction forces acting on the legs to drive the robot around. So it follows a simple Lagrangian dynamics modeling over here, which is simplified by inertia tensor. The 6 degrees of freedom of the main of the center body, which is the position and orientation. We have some Coriolis and gravitational terms here. And then we have the generalized force formulation for the leg, the ground forces acting on the leg, Fg over here. And then since we have thruster, we also have the thruster components attached at the legs. We modeled it to be implemented at the leg end position, but it can be anywhere within the leg. So it follows the kinematic model here, and the ground forces formulations can be calculated from this leg end position in inertial frame over here. Then once the leg end position has been found, we can use a compliant ground model and a Strebech friction model to get the ground forces. So the compliant ground model simply define the ground like a large spring and damping system, a very stiff damping, and we just calculate that to get the normal force. And as a function of the normal force, we can get the friction, which is like in Strebech friction model, have it as a function of velocity. So it's like this belongs to the static region, and then this is the Coulomb friction, and then this is the viscous friction, and it's encompassed in this one single equation as a function of leg and speed. Next, we'll move on to the control algorithm. This is the overview of the controller algorithm used in the robot. This block over here is the state machine, and then we have the reference state generated by the waypoint, and then we have send control command and sensor feedbacks to the robot plan. So the control commands is defined here. So we have two modes of locomotion, which is the flying state and the walking state. So in the walking gate, we have a typical like walking gate, trotting gate over here. So it has a swing. It has two swing state, which is the two diagonal legs moving forward, and then like the opposite leg moving forward. And this is done open loop with open loop timing. So it's kind of like a fixed gate cycles. And depending on the next waypoint, it has to transform between the two modes, and it has this transformation sequence here between walking to UAV and UAV to walking. The transformation is done open loop timing, so it has no control feedback control inside, but it just follow a predefined transformation sequence. So next we'll be explaining about the ERG, which is what we use to satisfy the ground friction constraint. So the idea is that we have a constraint equation here that's we have to find, we have to derive. So if you can derive the ground friction values as a function of the reference states, then if you can develop it in this formulation, then we can use the ERG method found here. So the idea is that we have a reference, and this is our target reference, and this is our current reference. So we want and this line here represents the constraint value. So we want the reference to be always within this region, such that so basically inside this region the constraint is satisfied, and we basically wants to get to the closest point to the target reference without breaking the constraint. So the idea is that we have some update law here, represented by VR, VN, and VT. VR basically tries to get to the target reference straight, but once it gets to this boundary, it wants to slide sideways to this nearest point to this reference. So we simply using some sort of Lyapunov formulation to achieve this, and the more detail can be seen in the paper. Next, we'll move on to the path planning algorithm. So we utilize the Probabilistic Road Map version implemented in our robot to allow multimodal locomotion. So in here, like in the top graph here, like this is for example, if you discretize the world into uniform grid, it will have way more points than if you're using a PRM algorithm over here. So as I mentioned, we modify the PRM so that it has ground and aerial nodes. So in this case, like we have the ground nodes in black over here and the aerial nodes in blue. After that, we can determine the edges such that like no two nodes like intersect. It doesn't allow the robot to intersect between this the obstacles, so as that once we have this roadmap configured, like and the edges configured, we use an A-star algorithm to find the minimum energy solution to get from the current position to the final position. So in this slide, there are several example environment that we use this multimodal PRM algorithm with A-star to find the minimum energy path from the current position to the target position here. Current position is blue, target position is green. The red blocks indicates a non-walkable platform or obstacles, and the green one is something is a platform that you can land on. So in this case, like in the environment A, there's this fully unwalkable terrain throughout this entire column here. So the robot simply walks here and then fly over to this platform. Same with environment B, like there's a fully unwalkable area here, so it flies over that and then it walks over to this final position. Environment C is similar to environment A, but with a longer distance between the unwalkable path to the platform. But as you can see, like it figures out that the non-minimum energy path to take is to simply fly over to the platform and land over there. Next, we'll show the simulation results on the path planning and the robot walking and flying, transform and flying to the platform. So this is based on environment A from the previous slide. So we have one fully unwalkable column of obstacle here. So the robot starts over here and it will perform a simple turn and move forward maneuver. So it's like it's a very simple walking gait over here. So we have a simple turn in place and walk forward. So that's what the robot does, and it's like it follows the path. And then over here, it transforms to the UAV mode and fly over this unwalkable terrain and land on the platform, transform back to the walking, and then walk to the final position. The tracking shown over here, it's pretty decent, and we can show how it works in the video in the next slide. So it's a video of the robot walking. As you can see, like it's a forward and move forward and turning in place maneuver. The walking gait is a simple walking gait using that ERG algorithm mentioned earlier, and the robot managed to get to the transformation point, and then it transformed to UAV, fly over to the waypoint and land, transform back, stand up, and walk again to the final place. So that's it for our presentation. In conclusion, we have developed a path planning algorithm for a multimodal legged and aerial robot, and we have implemented both the path planning and the controller algorithm inside a simulation. It shows in the simulation that it can navigate in this examples, unstructured terrains, and it shows that it can figure out the most efficient mode of locomotions to use to reach the target position. So this is all done in simulation. So in future work, we have to implement it to the actual robot, and the robot is currently under development, and we're working towards on getting a working prototype soon. That's it for our presentation today. Thank you for listening and have a great day.